Hi everybody, this is a lecture on sections 3.1 and 3.2. So given an n by n matrix A, the determinant of A is defined as follows, and it is denoted by just like this, that A. Now, just a little bit of a forewarning here. This is not really the definition of a determinant. I mean, it's equivalent to the definition of a determinant, but the real definition of a determinant is much more elegant than this, but it requires discussion of matters. It takes a little while. So you wouldn't really get the real discussion of what a determinant is unless you take, gosh, modern algebra, I would think, Math 4510, or if you go to grad school in math. So there's just a little bit of unfortunately it has to be this way. So the determinant is defined as follows. So with a 2 by 2 matrix, determinant A, or like that, absolute value A. For a 2 by 2, not that it has to be positive. For a 2 by 2 matrix A, B, C, D, like this, the determinant of A, right, and we write it like this, A, B, C, D with these vertical lines, is AD minus BC. Good morning. So we've seen this AD minus BC quantity before, remember? And when we talked about the inverse matrix, it's 1 over AD minus BC. What was it? DA minus B minus C, right? So the determinant for the 2 by 2 matrix appeared there. And then for a 3 by 3 matrix and higher, A equal to, so we'll write it like this, A, B, C, D, E, F, G, H, I, right? We define the determinant of A, right? And it's also written like this, A, B, C, D, E, F, G, H, I, to be equal to. So what you do is you pick a row or a column. A row and a column. So we'll pick, say, like row 1 and column 3. Like that. Row 1 and column 3. Or I'm sorry, pick a row or a column, right? So row 1, we'll say. So now you take the element in row 1, column 1, A, and then if you cross out that column, you're left with this 2 by 2, EFHI. So EFHI. And then minus B times the 2 by 2 matrix that's left over after you strike out that column, DFGI. Notice that we have a minus here instead of a plus, minus B. and then plus C, strike out its column, and you're left with D, E, G, H. Okay, so for a 3 by 3 matrix, it's defined this way. So you pick a row or a column. So we started with, say, row 1. Okay, you could also do it equivalently like this. So let's just copy it over. So now I'm going to pick a different row or column. So now I'm going to pick column 2. Pick column 2. So the determinant of A is equal to, so now take column 2, strike out row 1. So it's minus 1, and then this is what? Row 1, column 2. Row 1, column 2. And the 2 by 2 matrix left, or times B. And the 2 by 2 matrix left over is DFGI. DFGI. Plus, now take the next row, DEF. Okay, and strike out that. Now, do I use plus or do I use minus? Well, this is column 2, row 2. So it's minus 1 to the 2 plus 2, which happens to be plus 1. And the 2 by 2 that's left over is ACGI. Plus minus 1, strike out the last row, row 3, to the column row 3, column 2, and the 2 by 2 left over is ACDF. ACDF. Or equivalently, oh, and this turns out to be, let's write it out without these. So this is minus B, D, F, G, I. Oops, I forgot the E here. H here. All right, so 2 plus 2, 3 plus 2. E and H. So it's minus B times the 2 by 2 determinant DFGI plus E times the 2 by 2 determinant ACGI minus H times the 2 by 2 determinant ACDF. Or equivalently, let's do it a third way. Oops. Alright, copying over, well, I guess there's no space on that page. Or equivalently, A equal to A, B, C, D, E, F, G, H, I. This time let's do it around the third row. Okay, so this is going to be done as follows. The determinant of A is equal to, so strike out the first column, so that's G to the 3 plus 1, that's plus G, times the 2 by 2 B, C, E, F. Strike out the next column going with that row, right? And that's minus 1 to the 3 plus 2, which is odd. So minus h times the 2 by 2 ACDF plus I times the 2 by 2 ABDE. Right, so picking any row or column, you can calculate the 3 by 3 determinant in this way. Okay, this one is called the cofactor expansion. On row 1. This is the cofactor expansion on column 2. And this is the cofactor expansion on row 3. And these are all the same. No matter which row or column you pick, it's always the same. Is chosen, the determinant will always be the same. We can't prove this because we lack the real of a determinant. So, I mean, the reason for it is because the real definition of the determinant just implies it fairly easily. But, here we have that. And then for a 4 by 4 determinant, all right, so if you have a 4 by 4 matrix, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, this is equal to, well, again, you pick a row or pick a column. So I'm going to pick row 2. All right, so striking out column 1, it's e to the 2 plus 1, which is odd. So minus e times the 3 by 3 that's left over. B, C, D. J, K, L. N, O, P. Next column, so that's plus F, so it alternates, minus, plus, minus, plus. A, C, D, E, G, H, or oops, not E, G, H, sorry. I, K, L, M, O, P. Minus G times the 3 by 3 ABD, IJL, MNP. One more step. Can I squeeze it in? On one line. Oh, I don't know what to do. And then the last column, H, so it's minus, plus, minus, plus, H times the 3 by 3 left over, ABD, ijk, mno. Okay? And you can do that cofactor expansion around any row or column. So, and it doesn't change the value of the determinant. So let's take as an example the following. How about the determinant of the 3 by 3 matrix, 1, 5, minus 3, 2, 0, 1, minus 1, 1, 4. So we'll do the cofactor expansion around the first column. So we'll do cofactor expansion around the first column. So that is 1 times the 2 by 2 determinant, 0, 1, 1, 4. Minus 2 times the 2 by 2 determinant, 5, negative 3, 1, 4. And then plus negative 1 times the 2 by 2 determinant, 5, negative 3, 0, 1. Alright, so this is equal to 0 minus 1 minus 2 times 20 plus 3 minus 5 minus 0. Alright, so this is equal to minus 1 minus 46 minus 5. So that's minus 52. Okay? I think I did something wrong. So that's 0 minus 1, 20, 5 negative 3, 1, 4. So 20 plus 3 minus 5 negative 3, 0, 1. No, I guess that's right. So minus 52. All right, let's calculate it a different way, expanding around a different row or column. This time we'll do, let's say, row 2. Now, you only have to do this one way. I'm just giving you examples to do it, several ways to show you that it always comes out to be the same thing. So this is 2, so strike out the first column. So this is 2, and then this is row 1, or row 2, column 1. 2 plus 1 is odd, right? So it's minus 2 times the 2 by 2, 5, negative 3, 1, 4. Strike out the next column, 0. 0 times whatever 2 by 2, so you don't have to worry about that. And then minus the last one, right? It goes minus, plus, minus. 1 times the 2 by 2, 1, 5, negative 1, 1. Calculating that, we get minus 2 times 20 minus 3, so it's 20 plus 3, plus 0 minus 1 minus 5. No, 1 plus 5. Uh, 1 plus 5. So what do we have? So that's minus, that's 23, minus 46, minus 6, right, is minus 52. Okay? So that's a couple different examples. We expanded around the first column, got minus 52. And we expanded around the second row and got the same thing, minus 52. Okay? And you can expand it around any row or column, get the same thing. Here's another way to calculate a 3 by 3 determinant. So another way to calculate a 3 by 3 determinant is as follows. A, B, C, D, E, F, G, H, I is equal to, rewrite this 3 by 3 matrix and then put next to it the first two columns. A, D, repeat the first two columns. B, E, H, like that. So this only works for 3 by 3, but I mean it's a nice shortcut, so it's worth mentioning. So when you do that, after you've drawn them like that, there's 9 diagonal lines. There's this diagonal line, this diagonal line, this diagonal line, or sorry, 6 diagonal lines. This diagonal line, this one, which are sloping down to the right. And there's this diagonal line. Let me not use red, let me use green. This diagonal line, this diagonal line, and this diagonal line, which are sloping up to the right. Okay, so the 3 by 3 determinant is the sum of these products minus the sum of those products. So it's AEI plus BFG plus CDH minus minus GEC minus HFA minus IDB. Right, so the downward products are added and the upward products, everything going to the right, are subtracted. So let's take that same matrix that we were working with up here, and let's calculate its determinant this way. So drawing those first two columns, 5, 0, 1, and we've got the downward products. So that first one is 0, second one is minus 5, right? So 0 plus minus 5 plus the last one is minus 6. Minus, and those upward products to the right, 0, 1, and then 20, 40. All right, so minus 0, minus 1, minus 40. So the sum of all these things is minus 11, minus 12, minus 40 is minus 52 again. All right, so that's just for 3 by 3. It doesn't work for 4 by 4. But you know, it's a nice shortcut. So you can actually calculate the determinant more quickly than doing a cofactor expansion with 3 by 3s. Okay. All right, so enough talk about the definition. What is special about determinants? Okay. given a triangular matrix, so a matrix is triangular, when everything below the main diagonal is 0. So it looks like this: A11, A22, A33, A44, A. So this is a 5 by 5 triangular matrix. And here, these are just any entries here. But here, everything is 0. So we'll call this T. And when you have a triangular matrix, the determinant of T is just the product along the diagonal. It's A11, A22, A33, ANN. It's just the product of the numbers along the diagonal. And you can do that you can see that by doing the cofactor expansion around the last row, right? So the cofactor expansion along the last row, every term is 0 except for maybe the last one. That's going to be A55 times, right, the A55 times the 4 by 4 determinant of this matrix, right, which is then going to be A44 times the 3 by 3 determinant of this matrix, which is then going to be, so on and so forth, like that. So just by doing the cofactor expansion along the last row in an iterative fashion, you get that the determinant is equal to this. Okay. So this is a matrix that's called triangular. You will notice that if an n by n matrix is in row echelon form, then it must be triangular, right? Because the leading coefficients need to go strictly to the right in every row. So given that this one is non-zero, this has to be 0. And given that that's non-zero, or maybe further on in is non-zero, right? All the non-zero entries are forced to be, in the upper triangular part of the matrix. All right. So some special properties of determinants are as follows. So the main question that we want to ask ourselves here is what effect do elementary row operations have on determinants? Again, it's a little bit hard to prove these properties without the proper definition of what a determinant is. But we'll do our best here. We'll explain it more for 3x3 matrices, and then just sort of trust that it carries over to 4x4 and higher. Let A and B be n by n matrices. 1. If B is obtained from A by exchanging two rows, then the determinant of B is equal to the negative of the determinant of A. 2. If B is obtained from A by multiplying a row by a scalar k, then the determinant of B is that scalar times the determinant of A. 3, this is the most surprising one, I think. If B is obtained from A by adding a multiple of one row to another, then the determinant of B is equal to the determinant of A. It has no effect on the determinant itself. Okay, so the effects of elementary row operations, okay, are predictable. They are predictable on determinants. The effect of elementary row operations on determinants is very simple. Switching a row, you just negate. Multiplying one row by a constant k, right, multiplies that determinant by k, magnifies the determinant by k, right, or contracts that determinant by k. And then the main elementary operation of adding one row to another doesn't change the determinant at all. Okay, so let's prove this just for 3x3 matrices. So here is an illustration using 3x3 matrices. So switching rows. Right, so if I've got the 3x3 matrix, and here I'll use the formal notation, A31, A32, A33. Okay, what's that determinant equal to? Right, well, it's the let's do the expansion around row 1. So it's A11 times the 2x2 determinant, A22, A23, A32, A33, minus A12 times the 2x2 determinant, A21, A23, A31, A33, plus A13, oops, A21, A22, A31, A33. So let's switch rows 1 and row 1 and row 2. So A21, A22, A23, A11, A12, A13, A31, A32, A33. Since I switched rows 1 and row 2, okay, I'm going to do the cofactor expansion now. So this cofactor expansion was done around row 1. Now I want to do it around row 2. But that's exactly the same as this one, except that the plus minus plus pattern becomes minus plus minus. All right, so this is going to be equal to minus A11 plus A12 minus A13 times those 2 by 2 determinants. Right, because the coefficient plus 1 or minus 1, right, this is row 2, column 1, so it's minus 1 to the 3, which is minus 1. But here it's row 1, column 1. 1 plus 1 is 2, so it's minus 1 to the 2, which is plus 1. Right, so this is exactly the negative of that. So now you might be thinking, well, what if we switched rows 1 and row 3? Then the plus minus plus pattern doesn't change. Right, but then if you switch rows 1 and rows 3, then you've switched row 1 and row 2 in each of the 2 by 2 determinants, and so you get the same result. Okay, so that's switching rows, multiplying a row by a constant. So if I take this and I multiply everyone in row 1, say, by k, let's see if I can't make that look a little nicer, KA11, KA12, KA13. So now when I do the cofactor expansion for that one around row 1, right, I get the exact same cofactor expansion as before, except there's a k in front of every term. Right, there's going to be a k here, a k here, and a k here. All right, which is equal to k, just factoring out the k, times the 3 by 3 determinant that we originally had. Right, you just factor out the k, and that's the original 3 by 3 determinant multiplied by k. Adding one row to another, so this one, let's write it like this, A11, A12, A13, and then we'll say A21 plus KA11. So we're adding k times row 1 to row 2. So we need a little more space. So A12 plus KA11 A22 plus KA12, A23 plus KA13. Right? I added K times row 1 to row 2. And this is A31, A32, A33. So that 3 by 3 determinant will take the cofactor expansion around row 2. And what do we get? We get minus A12 plus KA11 times the 2 by 2, A12, A13, A32, A33. So let's go down a line here. Plus A22 plus KA12 times A11, A13, A31, A33 minus A23 plus KA13 times A11, A12, A31, A32. Alright, so this is equal to, well, it's A12 minus A12 times this, A12, A13, A32, A33, plus A22, A11, A13, A31, A33, minus A23 times this one, A11, A12, A31, A32, and then plus K times A11, A12, A13, A32, A33. Let's see, I need to go down a line with this. I guess that was a minus. Minus this plus KA12 times the same 2 by 2. A11, A13, A31, A33 minus KA13, A11, A12, A31, A32. Alright, well, this right here is just the entire 3 by 3 determinant of the original matrix. So that's equal to the determinant A11, A12, A13. Alright, that right there is the cofactor expansion for this 3 by 3 determinant. Right, the original matrix before I added K times row 1 to row 2. And then this one, well, unfortunately we have to multiply it out. So this is A12, A33 minus A13, A32 plus KA12 times A11, A33, A13, A31 minus KA13 times A11, A13, A11, A32 minus A12, A31. All right. So K, A11, A12, A13. A13, A11, A11, A12, A33. Oh, that's a minus. A11, A12, A33. So this cancels with that. And then this is plus A11, A13, A32 minus A11, A13, A32. So this cancels with this. And similarly, A12, A13, A21, negative is positive A13, A12, A31. So this cancels with that. So that whole thing is 0. So that's just equal to this 3 by 3 original determinant. A nice consequence of this is the following. Of this predictable effect of elementary row operations is the following. If A is an n by n matrix and E is an elementary n by n matrix. All right, so if A is an n by n matrix and E is an elementary n by n matrix, then the determinant of A times E, or sorry, if you multiply it on the left, if you multiply an elementary matrix on the left, it does that row operation to A, right? But E is obtained from the row operation applied to the identity matrix. And the determinant of the identity matrix is 1. So if you switch rows, it's negative 1. If you add one row to the other, it's still 1. If you multiply by a scalar, it's k. Right? Because you're just multiplying some row of the identity matrix by k, so that determinant is k. So this becomes determinant E times determinant A. So let's do an example. Let's calculate a 4 by 4 determinant using a row reduction to a triangular matrix. So let's calculate 0, 3, 1, 0, minus 2, 1, 0, 0, 4, 0, 0, 4, 1, 0, minus 1, 2. So let's calculate this determinant. So the first thing I'm going to do is I'm going to switch rows 1 and rows 4. 1, 0, minus 1, 2, and that negates the determinant. 1, 0, minus 1. Oops, no. 0, 3, 1, 0. So now I'm going to add row 1 twice to row 2, and it doesn't affect the determinant. So that's 0, 1, minus 2, 4. Subtract it 4 times from here. Oops, I'm sorry. That negative sign should still be there. Subtract 4 from here, for this row 1 from row 3. So that's 0, 0, plus 4, and then 4 minus 8 is minus 4, 0, 3, 1, 0. All right, so that didn't change the determinant, but I still have this negative out front. Now I'm going to add or subtract 3 of row 1 from row 4. So that doesn't affect the determinant again. 0, 1, minus 2, 4, 0, 0, 4, minus 4, 0, 3 minus 3 is 0, 1 plus 6 is 7, and then 0 minus 12 is minus 12. So now what I'm going to do is so think of this as factoring out. I'm going to factor out a 4 from here, from row 3. 0, 1, minus 2, 4, 0, 0, 1, minus 1, 0, 0, 7, minus 12. All right? So this determinant is 4 times this determinant. So you think of it when you're doing the row reduction as factoring out. You're sort of doing that thing in reverse. This determinant is obtained by multiplying this determinant by 4, because this row is obtained from this row by multiplying by 4. All right, and then I'm going to subtract 7 of row 3 from row 4, and that doesn't change the determinant. 0, 0, 1, minus 1, 0, 0, 7 minus 7 is 0, minus 12 plus 7 is minus 5. So this is minus 4, and then the determinant of this one, because it's triangular, is just this product. It's 20. All right? So this gives us a way of calculating n by n determinants for like higher than 3, for n higher than 3, in an easier way rather than that cofactor expansion. Okay. And then the last fact I want to talk about is the following. Given two n by n matrices, A and B, the determinant of A times B is the determinant of A times the determinant of B. And the proof is as follows. We have already shown that the determinant of E times A is the determinant of E times the determinant of A, when E is an elementary matrix. Right? We have already determined that when E is an elementary matrix. So now, if A is an invertible matrix, we showed in Chapter 3 that A is equal to a product of elementary matrices, where each EI is elementary. If A is not invertible, then A is equal to E1, E2, EM, where, well, I guess I should call them something different now. F1, F2, FT, Z, where each F is elementary and Z has some row of all zeros, right? We showed that a matrix is invertible if and only if it reduces to the identity, if and only if it has n pivots. An n by n matrix is invertible if and only if it has n pivots. So essentially, the fact that elementary matrices satisfy determinant AB is equal to determinant A, determinant B, implies that the identity holds for all matrices. Because every matrix has a factorization using elementary matrices. Furthermore, if A is invertible, then the determinant of A is equal to the determinant of elementary matrices, each of which is -1 plus or minus 1, each of which is plus or minus 1 or plus or minus k for a non-zero k, which is not 0. And if A is not invertible, then the determinant of A is equal to the determinant of those elementary matrices times the determinant of Z. But the determinant of Z must be 0. So, along with the fact that determinant AB is determinant A times determinant B, we also have the following fact. A is invertible if and only if the determinant of A is non-zero. So another characterization of invertible matrices comes from determinants, comes from pivots, and comes from determinants as well. Okay, so that's the end of the lecture on this section.